The multiplexer is to combinational circuits what a flip-flop is to sequential ones. It is pretty simple. It has two inputs, data and select lines. If we set the select lines as I, the ith input is mux to the output, as you can see by the truth table. If we set it as 0, it's D0, 1, D1 and so on. This is the symbol for a 2x1 mux. The multiplexer is the most basic element from which theoretically we can create any combinational circuit. This is because we can use a mux to make a NAND gate, which is a universal gate. This is as shown in this figure.
Anyway, let's code one and see how it behaves. Assign y is equal to d of s. This is how simple it is. I don't want to create separate files and modules for each kind of mux I want to use, which are 2x1, 4x1 and so on. I want just one file which instantiates the mux I want depending on some input. This is exactly what Verilog parameters are for. Data width is the width of the data line. If no input is passed, by default it would be 8. And cell width is the width of the select line. It is the log base 2 of data width. This is an inbuilt Verilog function. Let's simulate it. Looks like there are no errors. We can move on to coding the test bench. I'll include the includes file which has all the DUT files. Like I explained in the previous video, dump file and dump vars functions are for the waveform, are for creating the waveform file. The monitor statement will issue a print every time one of its variables changes. I'll instantiate the two or three different kinds of muxes now. For the 8 mux, we don't need to pass any parameter because the data width by default is 8. For the 2 mux, we need to set the data with as 2. This is how you do it. And I'll just create one more, the 32 cross 1 mux. I'm not gonna pass any output to it because that's not really needed. Inputs are enough. As for my stimulus, I am going to loop through the select values a couple of times. Let's compile it now. I haven't included it in my includes folder. Let me do that. Switch off this switch so that it switched to behavioral modeling. It's still not included. I need to rename it to muxbehavior.v. It should work now. Now y is mostly 0 because that is the bit being selected in all these cases. But I want it to be 1, so let me just tweak the stimulus. I'll put the delay after the assignment. Now it should be all 1. It is, except for the last bit. You see, when select line is 7, it doesn't actually enter the for loop, but it prints anyway because the monitor statement has cell as an input as well. So it actually is correct. Let's see how we can design a mux using logic gates now.
There are many ways of designing a mux, but the one which I prefer the most is the one derived from tri-state gates. We're going to be using tri-state buffers all over the project, so let's understand them first. A tri-state gate can be thought of like a switch. If B is equal to 1, then the switch acts like a closed circuit, so the output is directly transmitted to the input. And if B is 0, then the output is in high impedance. So this is going to be very useful when we start designing the system bus. And this is just the inverted version of it. Here's how we can use a tri-state gates to design a 2x1 mux. It's quite simple and elegant, isn't it? Now let's see how we can use this mux to design a 4x1 or an 8x1 or an n×1 mux. Remember when I said we can theoretically create any combinational circuit from muxes? That holds true for bigger muxes as well. Each n×1 mux can be split into two n/2x1 muxes. And the final output can be selected by another 2x1 mux, like this figure. So let's code this in Verilog now.
This time I'll add the structural model first to my includes file. First I'll create the 2x1 mux. It just needs 2 tri-state gates as shown in the figure. Tranif 0 is the inverted tri-state gate and tranif1 is the non-inverted one. A tranif1 gate with an inverted control input is the same as tranif0 gate. Now let's see how we can use it to create the bigger mux. So if data width is 2, I just want to instantiate this tri-state mux and call it a day. If it is not 2, we need to instantiate 3 muxes, one of which is this 2x1 mux and just 2 other muxes of n by 2 width. This is actually recursion, but in hardware. Each time a mux is instantiated, it will keep instantiating other smaller muxes until the input data width becomes 2. This is the end condition. At this point, it will instantiate the tri-state mux. Overall, the entire n×1 mux will be made up of these tri-state gates only. I will pass the upper half of the D input to the first mux and the lower half to the second mux. The select input should be the same for both. Everything except the uppermost MSP bit should be passed. I'll just declare a couple of wires to pass to the final mux. The MSB of the select bit should be passed here. Okay, let's simulate it now. I'll comment the behavior switch so that it switches to structural, and I shouldn't need to change the TB at all. I should get the same output, which I did. Now a word about these warnings. I got these warnings because I'm trying to put an 8-bit number into a mux which just expects 2 bits. So yeah, that's why I get these warnings. But in Verilog, the lowermost bits are passed by default, so it should be fine. And yeah, the output is same. Let's look at the waveforms just to be sure. All the muxes that we instantiated are present here. This is the D and S of the 2x1 mux. Select length keeps toggling because we are looping through it in a for loop. Let's look at the 8x1 mux, D, S and Y. I'll change it to a different color. The output is 1 because the select bit of the data is 1. Just like what we saw in the terminal. And similar to the 8x1 mux, here is the 32x1 mux with a bunch more of data inputs, and it is behaving in a similar way. That's pretty much it for muxes. Today we saw how to implement a mux using tri-state gates. In the future we will use these muxes to create all sorts of combinational circuits, maybe even the ALU. That's it. Thanks for watching.